Okay, today we're going to be looking at waves. And the reason why we're going to be looking at waves is because we're going to use light as a tool to try to figure out what's going inside the atom. So before we can use it as a tool to figure out what's going inside the atom, we have to figure out how it works. So we're going to look at light and the electromagnetic spectrum because light is part of the electromagnetic spectrum. And all of these guys are what we call waves. So let's take a little look at what waves are. There are several different phenomena, things that kind of we see around us that are actually wave phenomena. Okay, so these things have wave properties, so we have to learn some of the wave properties. Examples of wave phenomena, things that are wave phenomena, are just you see water waves. And when I talk about water waves, I'm not talking about the waves that are crashing the breakers at the beach. I'm talking right on the shore, but I'm talking about a little further out. So when you're in a boat and you're bobbing up and down, the reason that boat is bobbing up and down is because the water's coming by and it's got this little bundle of water we call a wave. And the wave goes up, then it comes down, it goes up again, and it comes down. So water comes waves. And it's probably the most visual thing that we see that allows us to kind of see what a wave is. But there are other phenomena that comes as waves. Sound comes as waves, and we can visualize it through a oscilloscope, which is a machine that allows us to go ahead and turn those sounds into some visual representation of that sound. There's light. There's things like radio waves that come out of your cell phones that come, to our radios. X-rays. There's a bunch of stuff that that uh, have wave activity. So let's take a look at what a wave is. So here is um, a depiction of a wave. This blue line, this light blue line here, goes up, comes down, goes up, and comes down. Why is it going up and down? It's describing something that's waving. In water waves, for example, it's the water that's waving. The water level goes up, then it comes down, and it goes up, and it comes down. So this is depicting the height or the elevation of a bundle of water, bundles of water, um, and at one certain point. So it looks like it's going across, but it's really just at one certain point. It goes up and down. Usually, the X here is the X um, uh, side right here depicts time. Okay, so the axis right here, the horizontal axis depicts time, and so the wave goes up, the water goes up, it comes down, goes up, comes down. So you can be at one spot, just going up and down like that. But as time moves along, you're going up and down. So in water, this represents the height of the water above the average sea level, let's say. In sound, this represents the pressure of the air in the area where the sound is being transmitted. Pressure increases, then it decreases. Pressure increases, and it decreases. In light, it's electrical and magnetic fields that get stronger and weaker, et cetera, and so on. So it's a cycling of something that produces this phenomenon. Okay. So let's take a look at parts of a wave. There are these parts. The crest is the peak of the wave. The trough is the bottom of the wave, the lowest point of the wave. And the wavelength, represented by this Greek letter lambda, is the length of a wave. And it can be measured from either the front to the back of a wave, or from crest of one wave to the crest of a second wave, or from trough to trough. And we usually measure it in meters. Unless it gets smaller or larger, then we could measure it in other stuff. We're going to be using nanometers a lot because light waves are very small. Okay, so let's go back to this so we can kind of see some of these things. These are the crests right here. These are the troughs, the bottom right here. This A right here stands for the amplitude, and that's just the height of the wave above the middle point or the average. And then as you can see right here, there's that Greek letter lambda again. That's the distance from crest to crest or trough to trough. If I were also to measure from like the beginning of a wave to the end of a wave, that's from here to here as it crosses the x-axis a second time. One time it crosses it going down, the other time it crosses it going back up. But since we started going up, really the corresponding point would be the second crossing as it's going up. So the distance from here to here would be the same. You could measure it in all those places, from one crest to the next crest, from one trough to the next trough, or from the beginning of the wave to the end of the wave. Really, any two corresponding points, as long as they're the same corresponding points. The thing about the term wave gets confusing because sometimes we use the term to mean a whole bunch of cycles or waves, and sometimes we can look at one cycle here. Notice that when there's wave motions, there's a repetition or cycling of the phenomena. And so as this gets bigger, then it gets smaller, gets down to the trough, and then it goes back up. We completed basically one cycle. It went up and down, and now we're back again. And so the next cycle is going to say do the same thing: go up, down, back again, up, down, back again. And so some people will consider the whole thing a wave. Some people will consider one of these cycles a wave. So that's where it gets a little confusing. In both cases, we will refer to waves in both cases, whether we're talking about the collections of cycles or one cycle at a time. All right. And the other vocab term we have to learn about is frequency. Frequency, uh, represented by the Greek letter nu. This is not a V. This isn't the greatest nu that I've ever seen, but because it usually has like a little tails to the left. It looks like the wind is blowing it to the left. But this is the Microsoft edition of nu. It's like a Greek M. So this is going to represent frequency. What is frequency? Frequency is the number of waves that pass a given point per second. So in this case, we're looking at one cycle as a wave, but you get several of them coming at. Um, we could measure them in these units called hertz, which basically means waves per second. So we can write it as waves per second or 1/second. Tells you in every second how many waves are passing a certain point. They've also been renamed after a guy named Hertz. Forget what his first name is, but his last name is Hertz. And so we went ahead and named this a wave per second a Hertz. Let me go ahead and demonstrate what frequency is. This is to differentiate it also from its speed, because people get speed and frequency confused. All right, so let's say that there's these two waves here. One wave has a smaller wavelength, the other wave has a larger wavelength. As you can see, the wave on the top here goes through a cycle much faster than the one on the bottom here. Actually, we're seeing what, one, two, like two and a half, almost three um, cycles in the top wave here. And here we're only seeing one in the bottom wave. So we say that the bottom wave here has a larger wavelength. The top one has a smaller wavelength. Now let's watch as these waves move, and they're going to move about at the same speed. So you can tell because if you look at the front of the wave, I'm going to keep the front of the waves going at the same rate. And we're going to see how many waves pass this line right here. So as the wave starts moving, we start get it moving to the right, and as you can see, they're both going the same speed. The front of the wave is still they're both waves. The front of both waves are at the same point, but we've got many more waves passing the line on top than we do at the bottom. Actually, at this point in time, only one wave is passed. The bottom wave, only one wave has passed the line, whereas in the top wave, we've got almost three waves have passed at this point in time. So we're getting more waves through that past that line in the top wave than the bottom. They're both moving at the same speed, as you can see. They both ended. The whole waves passed this line at the same time. So they were going at the same speed. We'll go ahead and rewind this again so you can see it again. They're going at the same speed, but many more waves pass through that point on the top wave. Why? Because it's a smaller wave. So if it's a smaller wave, the wave's going to pass through. It'll begin the second wave much more quickly, and then they'll get through that second wave. We can go ahead and measure these. If we assume that all this happened in 1 second, so we said something like, all right, this happens in 1/1000. All right, so that happened in 1 second. If you go ahead and count how many waves pass through here, if you count how many crests, let's say there's one, two, three, four, five crests in the top wave. There's only two in the bottom wave. So if all of them got through and it all occurred in a second, then we'd say that the top one has a frequency of 5 per second. You can also say 5 waves per second. A lot of times people just say per second, 5 per second, or 5 hertz. That these are both the same thing. 5 waves per second, 5 per second, or 5 hertz. Three different ways of saying the frequency of the top wave. The bottom wave only got 2 waves through there in the same time frame, so its frequency is 2 per second, or 2 hertz. Okay, and so this is how we go ahead and measure the frequency. As you can see, the frequency here is related to the wavelength. Right? Smaller wavelength gave us more frequency. And it's also related to the speed. If the waves were going at different speed, then we'd have a different number of waves going through. We just took 2 waves that were going at the same speed here. So there are relationships between these guys, and we can see them in a mathematical equation. And so here's the equation right here. This equation says S is equal to nu times lambda. Ooh, 2 Greek letters, right? Yeah, why do we use Greek letters? Because we run out of the our alphabet, right? The Latin alphabet, and so we need to. Uh, there's only 26 letters in the Latin alphabet. If we use capital and lowercase, that's only 52 letters, and there's more than 52 things to measure, right? So sometimes we have to dig into the Greek alphabet. And so once again, lambda here represents the wavelength of a wave. Nu here represents the frequency of the wave. And so we have that here. And if you take nu and you multiply by lambda, you will get the speed of the wave. Nu times lambda is equal to S, or S, the speed of the wave, is equal to nu times lambda. And if you have any two of these three variables, you can solve for the third, right? If you know the obviously if you know the frequency and you know the wavelength, you multiply them together and you'll get the speed. And it makes sense because remember that speeds are measured a lot of times in meters per second. So a frequency is in per second. Right? A lot of times we'll call it hertz, but when you put in these equations, you put it in waves per second, or 1/second, or second to the -1 as we have it here. Right? That's the same thing as 1/second. And when you multiply it by a wavelength in meters, you end up with 1/second times meters gives you meters per second, which are precisely the units of speed. Now, if you have the speed of a wave and you have either the frequency or the wavelength, well, then you can solve for the other. Right? If I know the frequency, then I just take the speed divided by the frequency, gives me the wavelength. If I know the wavelength, I take the speed divided by the wavelength, that gives me the frequency. Okay. And so we're going to do some sample problems so we can see how this whole thing works, practice problems like this. So we'll see how this works.